Hi guys, Miss O'Connell here. So today we're going to be discussing the conservation of energy. First, we'll review a little bit about what we looked at last week, and then we'll talk about how those three types of energies work together to create the law of conservation of energy. So this title here should look familiar to you. You most likely talked about it in chemistry. The form of the law of conservation of energy in which you look at in chemistry is most likely the first law of thermodynamics. In physics, we apply this concept a little bit differently than how you would have in chemistry. Okay, so let's get started with a review. Last week, you learned about three different types of mechanical energies. Okay, and you should have this written down in your notes. The first type of mechanical energy in which we talked about was kinetic energy, which is the energy of any moving object. So any object that is moving or has velocity has kinetic energy. The equation for kinetic energy is equal to 1/2 of the object times its mass times its velocity squared. We know that energy is measured in joules, mass in kilograms, velocity in meters per second. The second type of mechanical energy in which we looked at last week was gravitational potential energy, which based on that video, right, has to do with the zero line, meaning a reference point, and the final position of an object. Okay, so it's energy due to an object's position. Okay, and that position would be relative to that zero line. The equation for that, which you can use PE equals, but our textbook and many other textbooks use the symbol U, which is on the AP exam formula sheet. U sub G is equal to, okay, U means potential, G means gravitational, M is the mass in kilograms, G is the acceleration due to gravity on a specific planet. On Earth, it's 9.8 meters per second squared. On the moon, it's 1.63 meters per second squared. And H is the height, which is the distance or the displacement above the zero line. Okay, the third type of mechanical energy in which we looked at and we actually talked about in our Hooke's law and simple harmonic motion unit is the elastic potential energy, which is the energy due to the stretch or compression of a spring. Okay, so if a spring is in its normal state, meaning that it's not stretched or compressed at all, it has no elastic potential energy. Okay, if the spring is stretched, it has elastic potential energy. So if it's stretched beyond its equilibrium position, it will store energy due to its position. If it's compressed beyond its equilibrium position, it will again store elastic potential energy. The elastic potential energy is equal to 1/2 times the spring constant K, which is again the amount of newtons required to stretch a spring by a meter. K measures the strength of a spring. X is the stretch distance measured in meters, and we square that. Okay, and technically that should be a U sub S. S stands for spring. Okay, so the potential energy due to the position of a spring. Okay, we can use P capital E. The AP exam formula sheet uses U sub S. Okay, and that equation is provided for you on the AP exam formula sheet. Okay, so those are our three types of mechanical energies, okay, that we discussed last week. Those three energies, in addition to one more, which we'll talk about today, work together within a system. Okay, in a closed system, and which is frictionless, all three of those types of energies must be conserved. Okay, when there is friction involved, elastic potential, gravitational potential, and kinetic energy, in addition to thermal energy, which is the energy created due to the presence of friction or air resistance, the combination of those four types of energy will be conserved. Okay, we call that the law of conservation of energy. Okay, so the law of conservation of energy states that the total energy in a closed system must be conserved, must be constant. Okay, the sum before and after an event occurs or a collision occurs must be the same. So the equation that we get from that law would be that the sums of the initial energy in the system must be equal to the sums of the final energies within a system. The types of energies that can exist, if we expand that formula, we know that an object can initially have kinetic energy plus its gravitational potential energy initially, plus its elastic potential energy initially, must be equal to its kinetic energy final, plus gravitational potential energy final, plus elastic potential energy final, plus heat. Okay, if there is no friction, we can cross out the heat. Okay, if there is no friction, if it's a frictionless system or surface, or the problem tells us that we can ignore friction, we can assume that mechanical energy, which is elastic, gravitational potential, and spring potential energy, is conserved. Okay, so the conservation of mechanical energy, in the absence of friction, the total kinetic and potential energies of the system is conserved. So the mechanical energy is simply the sum of the kinetic, gravitational potential, and spring potential energy. Okay, so friction is what we call a non-conservative force because it removes energy from a system. Okay, if there is no friction, we can say that mechanical energy is conserved. If there is friction, the total energy of the system is still conserved. Okay, and those are our two sets of equations there. Okay, so let's take a look at a few examples. Okay, so if you want to follow along there, this problem actually comes from your book. A skier coasts down a very smooth 10-meter high slope, similar to the one shown in the figure. If the speed of the skier on the top of the slope is 5 meters per second, what is his speed at the bottom of the slope? Okay, so the words "a very smooth." Okay, so "a very smooth" tells us that there is no friction. Okay, so there's no friction in the system. If there was friction, they would give us a value for mu, which would tell us we need to consider friction. If it says frictionless, very smooth, okay, or omits a mu value, we can assume that there's no friction. Okay, so we're given the height of the slope and the speed at the top. So given that limited amount of information, we obviously cannot use F equals ma. We cannot use Newton's second law. But knowing the height at which a person or object begins and their final velocity or initial velocity, we can in fact determine, using conservation of energy, what that final speed will be. Okay, so we're going to use the law of conservation of energy. the sum of the initial energies in the system must be equal to the sum of the final energies in the system. Initially, you can see in the diagram that it's labeled. This gear has an initial velocity, v sub I, of 5 meters per second. Starts at an initial height of 10 meters. Okay, the skier ends on the 0 line, meaning ends at a final height of 0. We want the final velocity. So what kind of energy does the skier have at the top of the hill? Okay, so if he's moving, right, he has kinetic energy. If he's a distance above the ground, he has gravitational potential energy. Okay, so on the left side of our equation, we will leave kinetic and gravitational potential energy. On our right side of the equation, we know that heat, or thermal energy, is not a component of the system because the surface is very smooth. Our skier ends on the 0 line, so its final gravitational potential energy would be 0. Okay, so we can plug in what we know, but you might have noticed that mass was not given in this question. Take a look at the equation on the screen. We see that there's mass in each term. So, what could we do to eliminate the mass? Okay, so we could factor out an m on the left-hand side and then divide both sides by m. Right? And we see that the mass, because it's in each term, it will cancel out. Okay, so if you divide both sides by m, we see that they both cancel, and we're left with 1/2 times v initial squared plus g times the initial height is equal to 1/2 times the final velocity squared. Then we're going to plug in what we know. Okay, multiply both sides by 2 to get rid of that 1/2. And we simplify. So we have 12.5 meters squared per second squared plus 98 meters squared per second squared equals 1/2 times the final velocity squared. Simplify and multiply both sides by 2. So we're going to take the square root of both sides. So we take the square root of 221 meters squared per second squared, and we get that the final velocity is 15 meters per second. Okay, so the amount of energy that the person has at the top of its path must be equivalent to the total energy at the bottom. So the sum of the energy will remain the same, but the type of energy will change. So energy can be transferred from form to form, but it cannot be created or destroyed. So here, kinetic and potential energy were converted or transformed into solely kinetic energy as the skier approached the bottom of the hill. Okay, so the next one is a little bit more straightforward, but a different context. So example 2, a 5 kilogram cart moves up a hill that is 10 meters high. For the cart to reach the top of the hill, what is the minimum kinetic energy of the cart in the position shown? Ignore friction. Okay, so we know the cart starts on the 0 line, and it needs to move up a hill of 10. We need the minimum kinetic energy of the cart in the bottom. So what it's asking, okay, we assume that at the top of the hill, it has only potential energy. Okay, so at the top of the hill is only potential energy. We need to figure out what velocity it must have, or what kinetic energy it must have on the bottom of the hill in order for that to be true. Actually, we're going to change this equation. So we want the minimum velocity of the cart at the bottom of the hill. We're going to solve for the minimum velocity of the cart at the bottom of the hill. Okay, so similar to our last situation, just in the reverse order. Okay, it must have enough kinetic energy at the bottom to reach the top of the hill. So we're going to use the conservation of energy equation. We can reduce heat to 0 because we know that there is no thermal energy. Initially, at the bottom of the hill, what kind of energy will the cart have? Kinetic energy. Okay, at the top of the hill, the cart will have only potential energy. So we're going to plug in. We can set the initial potential equal to 0, the final kinetic equal to 0, and heat equal to 0. We are given mass here, so we can plug in and solve. So you have 1/2 times 5 kilograms times V initial squared equals 5 kilograms times 9.8 times 10 meters. We'll get 2.5 times V initial squared equals 490 kilogram times meter squared over second squared, which we know is equivalent to a joule. We get that by just multiplying our units across. Divide both sides by 2.5 kilograms. The kilograms will cancel. Take the square root of both sides, and we get that the initial velocity of the car must be 14 meters per second in order to reach the top of the 10-meter hill. Okay, so as we know, the AP exam has moved towards concepts mostly. So let's take a look at the takeaway points conceptually from today. Okay, so the total energy in a system must always be conserved due to the law of conservation of energy. In the presence of friction, aka a non-conservative force, it's called a non-conservative force because it removes energy from a system, mechanical energy would not be conserved, but the total energy would still be conserved. All right, so here's a list of equations that you still need to have on your note card. Okay, plus the addition of a few more. And that's it for today.